over to Luyan, who's going to talk about quantum error correction with binomial codes.
Okay.
Thanks.
Thank you, Maria, for the introduction. Can you see the slides now?
Yes.
Yeah. Okay. First of all, I want to thank the organizers for inviting me to this wonderful conference. Today, I will be talking about quantum error correction and error transparent gates based on a binomial bosonic code. This is the outline of my talk. First, I will briefly introduce the background of bosonic quantum error correction codes. In the earlier session, Liang has already given a very nice overview of this topic. Then I will quickly remind you the circuit QED system and the universal control of a bosonic mode. After that, I will present our work, quantum error correction based on binomial codes and error transparent gate under autonomous quantum error correction. Finally, I will talk about other quantum information processing applications based on bosonic modes, followed by a very short outlook and a conclusion. So this is a very well-known roadmap towards fault-tolerant quantum computation. At the physical qubit level, operations and simple algorithms have already been demonstrated in various physical systems. However, quantum information is fragile. Therefore, a practical quantum computer ultimately calls for operations on logical qubits protected by quantum error correction against unwanted errors. So one of the urgent goals is to realize a logical qubit with a longer lifetime than its individual components. Then we need to repeat at the logical qubit level what we have achieved at the physical qubit level, including gate operations, algorithms on multiple logical qubits. Finally, we hope we can reach the universal quantum computation. Extensive attention has been paid to the qubit-based quantum computation systems based on, for example, classical quantum error correction codes and the surface codes. Both these two approaches need to scale up to multiple physical qubits with a lot of resource overhead and then do the quantum error correction. There are a lot of experimental progresses along this line, including trapped ion systems, nitrogen vacancy centers in diamond, and the superconducting circuits. However, to have extended lifetime than the physical qubits and to have logical operations based on multiple qubits are difficult because the number of distinct error channels increases with the number of qubits, and also non-local gates on the collection of physical qubits are required. On the other hand, a harmonic oscillator is a single system and has infinite Hilbert space, large enough for redundant encoding. And most importantly, in this large Hilbert space, there is only one main error channel, the excitation loss. So there is only one error syndrome that needs to be monitored for quantum error correction. Since it is just one system, gate operations on the logical qubit is also simple. So bosonic codes are hardware efficient, and we can realize quantum error correction first, and then scale up for more complicated quantum information processing applications. A bosonic mode has actually long been proposed to store quantum information since the discovery of quantum error correction. And the famous one is the GKP code. And this year is the 20th anniversary of the original paper on archive. And the focus of this workshop is also on GKP codes. So we will hear a lot of talks on the GKP codes. A single harmonic oscillator is hard to do quantum control. So we need a nonlinear qubit to provide the necessary nonlinearity for universal control of the harmonic oscillator. And I will talk more on the control later on. In a superconducting system, we want to use a simple structure like this to realize a quantum error correction protected logical qubit. We have a microwave cavity to encode quantum information. A superconducting qubit couples to the cavity to protect and manipulate the stored information. And we also need a readout cavity to read out the state of the qubit. And besides the advantages of a harmonic oscillator, microwave cavities are ideal for quantum memories in the first place because they could have very long coherence times, much longer than the best superconducting qubit. And there are mainly three major bosonic error correction codes: the CAD codes, the binomial codes, and the GKP codes. And here are the Wigner functions of the typical codes in the code and error spaces. Quantum error corrections of these three codes have all been experimentally demonstrated. And the CAD code is the first one to surpass the break-even point. And the GKP codes have been realized in both the superconducting and trapped ion systems. And here, I will only focus on the binomial codes, which is our work. The binomial codes are proposed by Steve and Luyan. The code words could be expanded in the fork basis with binomial weights. And the general binomial codes can exactly correct loss, gain, and diffusing errors to specific powers. And the binomial codes have a few advantages. And the code basis states are exactly orthogonal and have exact equal mean photon numbers. So the code strictly satisfies the two basic quantum error correction conditions. And because the basis states in the code and all error spaces are orthogonal, the binomial codes could have explicit unitary operations for repumping energy into the mode. Finally, since the occupied fork states are truncated, unitary operations on the binomial codes could be more convenient and could have higher fidelities. And this is the lowest order binomial code, which is used in our experiment. And the logical zero is the equal superposition of fork 0 and fork 4. The logical 1 is fork 2. And as seen here, for the lowest binomial code, it can only correct a single photon loss error. And the recovery is needed immediately after each error detection. Otherwise, the information will be lost. And this is different from the CAD codes, which only require tracking the number of errors and a correction at the end of the whole quantum error correction process. And in order to tolerate more errors, for example, 2 photon loss errors, higher order codes with more information redundancy are required, but also with higher intrinsic error rate to bit. And this is actually the price one has to pay for any quantum error correction schemes. Redundantly encoding quantum information always increase either the number of error channels or the error rate. However, good control and the quantum error correction on the logical qubits hopefully can compensate this negative effect and eventually lead to better protection of quantum information with extended coherence. Now I'm going to go through the physical system quickly. And the cavity qubit coupled system is the so-called circuit electrodynamics architecture. And in most of the cases, the qubit and the cavity are largely detuned. So the system can be described by this dispersive Hamiltonian. And chi here is the dispersive interaction strength. And this is the energy spectrum of the system. And basically, we have 2 harmonic oscillators with different energy intervals corresponding to the ground and the excited states of the qubit, respectively. And on the right are the spectrum of each individual component. And because of the dispersive interaction, the frequency of one system depends on the state of the other one. So we can have controlled operations between the two components. For example, we can have qubit controlled cavity phase gate and photon number dependent qubit rotations. And combining the cavity displacement and the selective number dependent arbitrary phase, and we can realize the universal unitary control of the bosonic mode, I described in this paper. And another efficient approach for realizing universal unitary control is the optimal control technique, which explores the full control parameter space to optimize the control pulses. It is first developed in the NMR system and now has been widely used in experiments, especially in the superconducting circuit. And in the last decade, superconducting quantum computing also benefits a lot from the fast development of quantum limited parametric amplifiers, including JBA, JPC, and TUPA, etc., which allow high fidelity single short qubit readout. And the fast real-time feedback control is also very essential for measurement-based quantum error correction. And many groups have developed FPGAs with homemade logic to realize feedback control with very low latency, much shorter than the ancilla coherence time. Now with the high fidelity quantum non-demolition measurement of the qubit and fast real-time quantum feedback enhanced, and we can realize arbitrary quantum operations on an open quantum system. And in fact, quantum error correction is just open quantum system control that purifies the quantum state of a system by removing the entanglement between the system and the environment. And in a similar way, we recently demonstrated arbitrary quantum operations on the Qudit, and I will spend a few minutes to talk about it now. And for the d-dimensional quantum system, for example, a cavity, we can use the lowest several energy levels for the Qudit. And we can realize its arbitrary quantum operations with minimum extra resource, just a single ancilla and feedback control. And we can apply a unitary gate on the composite system, and which can be realized by the discussed snap gate or grip. And this unitary gate depends on all the previous measurement results of the ancilla. Then the ancilla is projectively measured with its binary outcome stored in a classical register, followed by reset of the ancilla to the ground state. And the new ancilla output could be used for the next round of new unitary gate. And after a few rounds, we can realize the arbitrary quantum operations on the Qudit. And to save physical resource overhead, and we can use a two-level ancilla and a binary tree method as shown here. And the circuit depth is only 2 times log 2D for the d-dimensional system. And for d equal 4, a 4-layer binary tree is enough. And in our experiment, we choose the lowest 4 levels of the cavity as the Qudit. And as an example, we demonstrate the quantum coherence manipulation of a Qudit. So this is what we do. And we first prepare a maximum coherent state in the Qudit, 0 plus 1 plus 2 plus 3. And then we apply a strictly incoherent operation, SIO, on the state. And finally use SIC PUVMs, the symmetric informationally complete PUVMs, to perform tomography of the output state. And here both the operations at SIO and the SIC PUVMs are realized with the binary tree method. And we can use a rank 2 SIO operation to partially remove the original coherence, or a rank 4 SIO to fully remove the original coherence in the Qudit. And here are the experimental results, which agree well with the ideal cases. And here I want to emphasize that the SIG-PUVM tomography is much faster and more efficient than the Euro-Wigner tomography of a cavity. And so this experiment demonstrates the advantage of arbitrary quantum operations in practical quantum tasks. And next, I want to talk about our quantum error correction experiment on the lowest order binomial code. And this is our experimental device, which is identical to the previously discussed one. It consists of a storage cavity for the binomial code, a transformer qubit as the ancilla, and a readout cavity. The ancilla dispersively couples to both cavities, and device parameters are listed here. And in our experiment, we realized the encoding, decoding between the ancilla qubit and the logical qubit. And we also demonstrate repetitive quantum error correction and a single qubit universal gate set and a Ramsey experiment on the logical qubit under continuous quantum error correction protection. And this is the protocol of our quantum error correction. We repeatedly perform parity measurements with a certain time interval to check if a photon loss error has happened or not. And according to the error detection outcome, we adaptively choose the appropriate control pulses to correct the logical state. And here we use a 2-layer repetitive QEC scheme, trying to minimize the induced errors by the imperfect error correction operation itself. And this is the experimental result. And the black curve is for the ancilla qubit only. This process is not error correctable. This qubit is not error correctable, and its decay is the fastest. The green one represented the binomial code with quantum error correction, and compared to the red one without quantum error correction, and we see quantum error correction indeed improves the coherence time by nearly 3 times. However, our error correction has not surpassed the break-even point yet, which is the blue curve defined by the fork 0-1 encoding. And this is mainly limited by the finite fidelity of the control of the code. And we also realized a universal gate set on the binomial code with an average gate fidelity of 97%, characterized by random benchmarking. And this is basically the current limitation to achieve break-even. And with the repetitive quantum error correction and the universal operations on the logical qubit, and we finally demonstrate a Ramsey experiment on the quantum error correction protected logical qubit. And the blue line is without quantum error correction, and the red one is with quantum error correction. And from the contrast of the interferences, we can see that quantum error correction can improve the coherence by a factor of 2. And since Ramsey interferometry has been widely used for precision measurement, and our result could be used for quantum error correction enhanced metrology based on logical qubits and quantum error correction. Well, besides the operation on a single bosonic code, universal quantum computation also requires 2 logical qubit operations. So the experimental architecture needs to be extended to 2 cavities. And entangling gates between 2 bosonic codes have also been realized. For example, the C0 gate, the E-swap gate, the C-phase gate, and even teleported C0 gate. So we can have a universal control of the bosonic codes. Now we'll move on to the error transparent gate on the binomial code and autonomous quantum error correction. And the previously discussed quantum error correction can protect the stored information from leading orders of error. Fault-tolerant quantum computation also requires to protect the dynamics of quantum information during each step of computing. And for this simple circuit, every part could have errors. The state preparation, single qubit gate, two qubit gate, and final measurement, or even during the waiting time could have errors. And to have useful computation, every part of the circuit should be carefully designed to keep errors from propagating and accumulating such that each encoded logical qubit can have at most one error and can still be well protected by quantum error correction. And for example, we should replace the physical qubit with the logical qubit, and we should have fault-tolerant state preparation, fault-tolerant error correction, fault-tolerant single qubit gate, two qubit gate, and even fault-tolerant measurement. And benefiting from the hardware efficiency property, the encoding, decoding, error corrections, and universal logical gate sets on encoded logical qubit have been demonstrated with the Bosonic code. So people can now experimentally explore the fault-tolerant operations on the Bosonic code. And here I want to note that the early attempts towards the fault-tolerant quantum computation are the demonstration of the literal meaning of fault tolerance, that is the capability of correcting certain physical errors during the gate operation instead of achieving the fault-tolerant threshold. And the ancilla play a significant role in realizing the operations on Bosonic codes. The damping and diffusing errors of the ancilla could induce significant errors on the Bosonic codes. For example, qubit damping error in the error detection circuit could propagate to the encoded information by causing a random phase shift, which cannot be corrected. So in this work, by introducing redundant energy levels of the ancilla, a fault-tolerant error detection against the ancilla damping error has been demonstrated. And this scheme is similar to use a quantum error correction protected ancilla system. And their experiment shows a suppression of the ancilla errors by a factor of 5. And to prevent error propagation from the ancilla system to the encoded system during gate operation, there's a theoretical work analyzes the conditions on the interaction Hamiltonian and define the concept of path independence. I think Luyan also introduced this this morning. And in this experiment, a path-independent phase gate with the snap technique is demonstrated, where the fidelity of the snap gate with the 3-level ancilla qubit is significantly improved by the specific path independence design. And this phase gate can tolerate both T1 and T2 relaxation of the ancilla. Besides the tolerance of ancilla errors during the desired gate operations, the errors occurring in the encoded system should also be considered and prevented from propagation. To ensure photon loss error will not propagate and the arbitrary unitary evolutions, the concept of error transparent gate is introduced by these two papers. And the basic idea is the following. Ideally, a quantum state should evolve unitarily in the code space under the gate Hamiltonian with a finite gate time. If an error happens during the gate, the evolution will jump to the error space, while the subsequent evolution in the error space is identical to that in the code space up to the global phase. So this error during the gate operation is tolerable by quantum error correction at the end of the evolution, and the gate can still be implemented successfully. And we just realized such an error transparent phase gate. And our experiment is also based on 1 qubit and 1 storage cavity. And the effective Hamiltonian is this, where we have neglected the dispersive interaction because the ancilla mainly remains in the ground state. And Ks here is the Kerr coefficient of the cavity induced by the qubit. And we also use a binomial code. And again, this is the code space, and this is the error space. And in the proper rotating frame, we can have force state remains stationary because our basis is 0 plus 4 with a fixed phase. The Kerr effect would induce an actual phase on fork 2. And this phase could give a phase rotation R Kerr of the logical qubit. And it would be useful in the code manipulation. However, the state in the error space rotate with different rates. And that is the Hamiltonian in the code and the error spaces are different. And the error transparent condition is not satisfied. So this gate is not error transparent. And in order to meet the error transparent condition, we use a technique called parse, namely the Photon-number-resolved AC-Stark shift. And by applying a continuous pump on the ancilla qubit that is detuned from the transitions, the AC-Stark effect would induce a photon number dependent energy shift. And as shown here, we realize shifts of different fork states as a function of the pump amplitude. Those are experimental results and the lines are theory. They agree very well with each other. So we can continuously and precisely tune the fork state frequencies. And with this pulse Hamiltonian under certain pump amplitude, and we could achieve the error transparent condition. That is the total Hamiltonian in the code and the error spaces are the same. And this can be seen from the Ramsey interferences of the states in the error and the code spaces. And the pulse could synchronize the regionally different oscillations and thus can eliminate the jump time dependent phase accumulation during the gate. And in this case, K prime is non-zero, and we have an error transparent phase gate, RET. And we can also add another pump to tune K prime to be 0. Another pump here to tune K prime to be 0, such that we can have an error transparent identity gate. And this error transparent realization of an idle Hamiltonian is also important because the Kerr effect could be shut off in this case, and quantum information can be protected by the binomial quantum error correction code from random photon loss error induced dephasing. Now we can demonstrate the performance of error transparent gates. And this is the protocol for the experiment. And we first encode an initial state, the logical 0 minus I logical 1. And then we apply 3 different gates. And we have 1 non-error transparent phase gate and 2 error transparent gates for different durations. And we can perform an error detection on the logical state after the gate. And finally, we perform Wigner tomography to characterize the final state depending on the error detection outcome. Here are the experimental results. And if there is no error, the 3 gates behave normally with the coherence maintained. And that's the left plot of each column here. However, if there is 1 error occurring, the results are shown on the right plot of each column. After a long time, the non-error transparent gate, the state after an error eventually loses the phase information and becomes a mixed state. For the error transparent gates, the coherence of the states in the error space is preserved because the final state is independent of the random occurrence time of error. And this demonstrates the error transparent property of the error transparent gate. And we also developed an autonomous quantum error correction technique to correct errors after the gate, instead of using error detection and feedback control for the recovery. And here we use one single unitary transformation to recover the logical information without an error detection by transferring the error entropy associated with the logical qubit to the ancilla. And finally, the ancilla is reset to the ground state to clear the entropy for the next round use. And the reset of the ancilla could be done with measurements and feedback or by engineered dissipation. Because the autonomous quantum error correction does not need error detection and therefore can avoid the latency in the electronic control system, this will greatly reduce the hardware requirement. And similar techniques have been used in these two papers, also in the superconducting circuit and trapped ion system. And I think we will hear more from Professor Wang and Ho in this conference. Now we can combine the two techniques, pulse and autonomous quantum error correction, to improve the gate performance. And this is the protocol. And we perform a gate followed immediately by the autonomous quantum error correction. And this is the total process fidelity as a function of gate time here. And the gray dotted curve is for non-error transparent gate, the R curve without quantum error correction, and could be regarded as a reference. And the autonomous quantum error correction definitely improved the gate fidelity to the black curve. And the ET gates show even better performance than the non-error transparent gate R curve with the autonomous quantum error correction. And the ET logical gate can be interleaved with autonomous quantum error correction and performed repeatedly for the continuous protection. And this is the process fidelity of this whole process as a function of time. And time is this repeated time here. And without quantum error correction, the encoded binomial code decays with a time of about 180 microseconds. Autonomous quantum error correction could improve it to 260. And by using error transparent gates, we could further improve the lifetime to 300 and 360 microseconds. So there's a factor of 2 improvement by combining the error transparency and the quantum error correction. So this is the error budget for the error transparent and non-error transparent gates. The lifetime here for the error transparent identity gate is shorter than that with error transparent phase gate. And that's because the extra ancillar excitation from the additional pump. And for future work, we want to complete the universal gate set for quantum computation in the same error transparent manner. And similar techniques should be able to be extended to realize the missing components, the error transparent Hadamard gate and the error transparent controlled phase gate. And in the last part, I want to talk about other quantum information processing applications based on bosonic mode. And during the last few years, the superconducting bosonic modes have been widely applied in quantum applications because of their advantages. So the first one is the mode can have infinite large Hilbert space that can be used for quantum error correction, as discussed already. And the bosonic modes could be realized with multiple degrees of freedom, and therefore they could be scalable. In addition, the bosonic modes are convenient in transferring information and also can easily interface with many different physical systems.
I'm jumping in, I'm sorry. Yeah, Luyan, just jumping in to say that 5 minutes, yes, sorry.
Okay, thank you. So So the bosonic modes are inevitable building blocks in quantum networks. And here is our recent review article summarizing the applications of the bosonic codes, including in quantum computing, quantum communication, quantum metrology, and quantum simulation. And we already talked about quantum computation. In the following, I will mention briefly some recent progress in the other three directions. In a quantum network, quantum information needs to be distributed among quantum nodes via either direct quantum state transfer or quantum teleportation through shared quantum entanglement. The bosonic mode in the cavity can be easily converted to the flying mode for transmission. Also, during the transmission, the dominant error is also the excitation loss. So the same quantum error correction technique can be performed at the receiver end to improve the communication fidelity. Therefore, bosonic codes are of great potential for building quantum networks. Proof of principle experiments of most basic quantum network components have been reported. For example, the stored bosonic codes in the storage cavity can be converted to a traveling wave packet through a coherent frequency conversion between the two cavities. And teleported CNOT gate, remote entanglement, and on-demand quantum state transfer have also been demonstrated. The ultimate universal quantum computation is still quite challenging. The use of noisy quantum systems in quantum simulation, on the other hand, could be useful in the near future. Compared with the qubit arrays, the bosonic modes are indispensable in many physical models, and they could be applied directly in analog quantum simulations. And as an example, the bosonic modes are applied to solve the vibrational structure of molecules. And bosonic simulators are ideal to establish direct correspondence between the photonic cavity modes and the molecular vibrational modes. Bosonic codes can also be used in metrology. And instead of using fragile two-mode entangled states, quantum metrology based on a single bosonic mode has been experimentally implemented in trapped ion and superconducting circuit. And this is our work. Using a single mode 0+n encoding, the sensitivity of a phase estimation can beat the classical limit by more than 9 dB at n equal 12 and approach the Heisenberg limit. However, this 0+n state is not error correctable. And in the later work, we use 1+n encoding, which does not meet the quantum error correction condition, but we can perform approximate quantum error correction. And we use this encoding to sense the microwave photons in another cavity. And the experimental results show the sensitivity as a function of the sensing time. And this black curve is to use 0+1, the best physical qubit in the system, as the sensor. And the blue curve is to use 1+3 as the sensor with no quantum error correction. And the red curve is with quantum error correction. And since we can track errors by grouping different trajectories with different numbers of errors, we can gain more information, and the sensitivity can be further improved to the purple one. So from here, we can see the bosonic quantum error correction has considerable potential for quantum metrology. And here's a short outlook. For the short-term research, we would expect further extensions of current bosonic systems and demonstrations of quantum advantages brought by bosonic codes. For example, we can explore bosonic codes in quantum repeater, quantum simulation, and quantum metrology with the near-term NISQ superconducting systems. And for the long-term goal of quantum computing, it definitely needs more efforts, and we need to further improve the coherence of the quantum system. Improvements of the superconducting materials and fabrication techniques always deserve continuous effort. The limited quantum gate fidelity is the main obstacles for demonstrating higher order bosonic codes that are able to correct more errors. And the fidelity loss mainly limited by the hardware imperfections, but advanced quantum control techniques should be developed and would be useful to improve the control precision. Universal quantum computation also requires the scaling of bosonic codes. And one possible approach is to concatenate the bosonic codes with other codes, like the surface codes. In the next few days, there will be talks on surface codes with Kirkhead qubits or GKP qubits. So here's the conclusion. I talked about the repetitive quantum error correction on the binomial code and error transparent gate on the binomial code and the autonomous quantum error correction. I also mentioned that the bosonic modes are fundamental and indispensable physical systems for quantum information processing. Also, bosonic codes are promising candidates for future quantum information processing. And finally, I want to acknowledge my collaborators, especially Changyun Zhou from USTC. I also want to thank Steve from Yale and Vijay from India and my other local collaborators. And I also have to thank my students and the funding agency. With that, thank you very much for your attention.
Thanks. Thank you, Luyan, for this nice talk. So we have a few, sorry. Yeah, we have two questions that I see in the chat room, so maybe I'll ask them very rapidly. So the first one from the organizers is that, do you think, so I guess it's related to your last slide about the outlook. Do you think we need to go to, I mean, in your outlook, are you gonna go to higher order binomial codes, or I guess you're gonna more investigate the concatenation? I guess that's perhaps the other option.
That's, well, these two directions definitely are possible. And for the higher order binomial code, and you will, as I said, you will be limited by harder control. And that's also, I think, the advanced quantum control techniques should be developed in order to do this, to do a high precision control of higher order binomial codes. And certainly for the concatenation of the binomial code or the bosonic codes with other, like repetition code, I think that could be the possible directions. I think, Mazir, you also have a very nice paper on this direction.
So, and so I guess that the second question is about the autonomous quantum error correction. So it's by Alain Sarlet. So he's asking if he says that in your entropy swap, it seems like clear if the psi error, the state, the error after the error is known and unique for each psi L. Are there special conditions here such that this holds? Are there any assumptions that you've made in this?
Sorry, maybe I didn't quite get.
I guess I believe, so if I understand correctly, so if you go back to the slide where you explain the autonomous quantum error correction, you have the state after the error, which is called psi error. So it says that if it is, I guess that we understand this when psi e is known, how this works, but how about if you have an error channel with psi e, which is not known? But I guess...
maybe I can jump in by mic if that's okay. Actually, I was thinking of when you were mentioning the fact that during a gate you could have a jump, and then this would give you a random phase, for instance. So in psi e, I could imagine, depending on the time where you have this jump, you could have different phases. And, and then it seems to me harder to imply that principle.
Yes, I think you are right. But in this, well, in order for this autonomous quantum error correction to work, and this error state, I think this, we also use this error transparent gate. And for this particular gate, and there will be only one global phase for the errored logical state, and which is independent of the occurrence of errors. So in that case, it doesn't matter, and we can correct. So in other words, this state is a unique state, instead independent of the error happening. So therefore this autonomous error correction technique can correct this error. Is that what I guess that's what you're asking, right? So
yeah,
we have to combine
very great.
transparent.
Combining autonomous quantum error correction with error transparent gates. That's a great answer.
Yes, that would be more effective.
That
would be more effective. Yeah.
Yeah, very interesting. Thanks.
Okay, so I guess there's still another question, but I don't think, maybe we don't have time. Maybe we'll have to switch to the next speaker. So Rajveer, I invite you to ask the same question perhaps in the Slack room. So it's about the Heisenberg limit, I think, of the metrology problem. So I would recommend that we follow up with the next talk, and maybe Luyan can take more questions in the Slack room.
Sure. Thank you.
Thanks. Yeah, thank you, Luyan. Okay. That's very nice.
Thank you very much.